Welcome, everyone. We'll give people another minute or so, and then we'll get things started. All right, the number is still going up, but I guess now is as good a time as any to get started. Welcome to the 28th WIN conference. It's hosted at the University of Minnesota. Some brief history. The WIN series began with the first meeting in 1973 back in Sweden. And since then, it has been held in 16 countries across 5 continents. And it will continue 2 years from now in July of 2023 in China. Keep an eye out for that. Let's see, I posted some links in the chat, the conference page, the history. I've also posted a link to the code of conduct, which we have all agreed to. Also, let's remember that, in this morning session, we have neutrino plenaries and then lecture week plenaries, but then also tomorrow, there will be asynchronous talks where you'll have a chance to discuss topics with a number of experts on neutrino and electro weak physics topics. Also, there'll be poster sessions and social interactions on Slack and GatherTown, which I've also linked if you've misplaced those in your emails. And we look forward to very interesting discussions with, on neutrino physics. So it's about time to begin. So our first speaker is Irina Mocioiu. She got her PhD at Stony Brook out here on Long Island. Her PhD was titled Topics in Neutrino Oscillations, Phenomenology of Non-Commutative Field Theories, and CPT Violation with Robert Schrock. She then went on to do a postdoc at Arizona on more neutrino physics and also black holes. And then she did a postdoc at Argonne before becoming a professor at Penn State University. And today she is going to tell us, she's going to give an overview of neutrino theory. So Irina, if you can go ahead and share your screen. The talk is 30 minutes with 5 minutes for questions. I'll give you a verbal warning at 25 minutes.
Thank you so much. I can't share because you're still sharing the schedule.
Yeah, whoever's sharing has to, there we go.
Thank you.
And
thank you very much for this opportunity to discuss a neutrino theory overview. When I was handed this, this title, I really wondered actually, what does it even mean? What am I supposed to talk about? So it was a little bit hard to even decide what is neutrino theory. And the bottom line is that I could give a full talk about any of these little titles in the little bubbles on this slide here. And even there, one talk wouldn't be enough. And then the connections between them are even more complex. So it's really, really impossible to cover even a small fraction of what we do in neutrino theory. So what I'm going to try to discuss is really just a little bit of all of this, the importance of all of these connections between different topics, from the big questions of the origin of neutrino mass and the nature of the neutrino, and then how we go from there to really connecting to experimental observables by going through all the other connections to neutrino interactions and new states and other types of particle physics. And then I'll pick just one small example of one model where I will discuss a little bit more detail. So really, the main message of this talk is the fact that neutrino theory is a very vast and complex subject. So most of the time in many conferences, you will get a full 1 hour talk just about a neutrino mass generation and flavor. And actually even here, we have to decide if these are one problem, one question, or actually multiple questions. We don't know that yet. But even for mass generation, there are some generic ideas that we've known about for a very long time, like seesaw mechanism. And then there are lots and lots of explicit models where we are trying to generate very specific realizations where you can obtain neutrino masses, mixings, CP violating phases, and potentially connections to maybe the quark sector as well in classes of models, for example, like ground unification, but not necessarily. So there are many types of classes of models. Primarily, again, ground unification was a very popular scenario, in which case it's most likely that the scale for the generation of neutrino masses is very high, somewhere around the gut scale or maybe a little lower, but still pretty high compared to electroweak and everything else that we've observed. Then there are other classes of mechanisms where you pretty much don't have a neutrino mass to start with. It's naturally zero, maybe because of some symmetry or some other reason, but then you generate it radiatively. So that's another way of explaining why it's actually small. And then there are other types of models which involve flavor symmetries, which say more about the generation of mixings and such. And many of these models actually cover either, as I said, very high scale, but also either TV scales where it's easy to connect to electroweak physics and other types of observables that we have outside of neutrino physics, but it's also possible to generate mass even at sub-eV scale. And pretty much you will find one idea or another everywhere in between. And that's one of the biggest questions that we have right now in neutrino theory, which is what is the right scale for neutrino mass generation? And as I already mentioned, mass generation is one aspect that we're interested in, but one of the biggest questions that we have is really the nature of the neutrino and overall lepton number. Is lepton number a conserved quantity or not? In the standard model, it's always conserved. It's an accidental symmetry, but we have good reasons to believe that maybe neutrinos are special, and maybe that has something to do with the fact that they're Majorana fermions. And even this is maybe an additional question, because we don't fully know if the nature of the neutrino is very intrinsically related to the mass generation mechanism or not necessarily. But this is definitely one of the biggest questions that we have, which is the neutrino a Majorana fermion? And especially, how can we tell that? And I will get back to this, how we need both observations and a lot of theoretical developments to fully understand the connections. And of course, one obvious connection that we can ask about and explore consequences about is the connection to maybe dark matter or baryogenesis through leptogenesis or through other means, where again, dark matter and all the astrophysical and cosmological observations are the other observations which prove the existence of physics beyond the standard model, in addition to the existence of neutrino mass and mixing that we already know about. So that's one thing to be explored. And of course, all of these scenarios in any given explicit model, depending on the scale where the new physics is that leads to the neutrino mass generation and the flavor structure of the lepton sector, you can try to explore and understand the connections to all the other particle physics that we already know about, which involves either collider type of physics or flavor physics in the quark sector or charged lepton sector, baryon number violation. And again, how these connections actually look like have to be explored in detail in every single one of these classes of models, where if you have very high scale physics, then you're more likely to connect to things like baryon number violation. If you have TV scale physics, then it's more likely that the Higgs sector will know something about it, and so on. So all of these connections have to be understood within each class of models in order to be able to go from here ultimately to really the experimental observations, which can tell us if our ideas are likely to be the right ones or maybe not, or how to actually modify them such that they correspond to real nature. And just to say a few words about astrophysics and cosmology, again, you can give many, many talks about just this, but I won't have time to cover that. I just wanted to briefly mention there are lots of neutrinos in the early universe. We know they play an important role, so that's something that's interesting to explore, both in terms of how neutrinos affect cosmology and in terms of how cosmological observations can help us learn about neutrinos. Then another example would be supernovae, where again, there is a lot of astrophysics and a lot of neutrino physics involved. Neutrinos are the main transporters of energy out of the supernova, so they affect the dynamics of the explosion itself. They affect a lot of things within the supernova. And by observing those neutrinos, we can hope to actually learn about neutrino properties in addition to the astrophysics to the dynamics of the supernova explosion itself. And one thing to remember is that over the last couple of decades, actually, we've made a lot of progress in understanding neutrino oscillations inside supernovae, but we haven't answered all questions by a long shot because neutrino oscillations inside a supernova are extremely complex. It's a pretty extreme environment with very, very, very many neutrinos. And because of that, in addition to standard neutrino oscillations through matter, you also have self-interactions of neutrinos playing a role, and those can give rise to all sorts of interesting phenomena. And in addition, the matter itself is a very dynamic environment where everything is moving and changing. So you have all sorts of interesting shock waves or other changes in densities that can lead to and rotation and so on, which can lead to a very, very complex phenomena, which are very interesting to understand. In addition, I already mentioned possible connections to dark matter and baryogenesis that we need to better explore. And of course, we now have detected very high energy neutrinos, and we hope to detect a lot more. So in addition to telling us a lot about astrophysical sources, which are pretty extreme environments, again, very interesting and not very well understood, we also get access to very high energies and to understanding this propagation over extremely large distances to these sources, which again allow sensitivity to all sorts of neutrino properties that we couldn't otherwise access. So each of these can become pretty much a neutrino theory talk on its own, but I won't say any more about this for now, and go back again to how do we go from the big questions of what is the origin of neutrino mass, what is the nature of the neutrino, to really experimental observables that can tell us something at least about the scale or about the type of model that we should be considering or more. And I'll go through a few of these possibilities of how we can connect these big questions to the actual data. One obvious thing that I will talk a lot more about later, that's what I'll focus on a little later, are neutrino interactions. And in some of these models for neutrino mass generation, new interactions are predicted. Of course, depending on the scale, this might be really, really weak. If physics scale is extremely high, then probably these new interactions will not be observables. But if they're not extremely high, then these interactions might be relevant, and they might give us a connection between the actual mass generation models and experimental observables. Though I will talk more about neutrino interactions in general later. They also typically predict new states. You have at least new Higgs sectors, and maybe you also have new neutrino states. sterile states, right-handed states, which again might be very heavy, in which case we don't have access to them, might be very light and directly observable in experiments, or they might be not too heavy, but not light enough to actually observe directly, in which case their presence might manifest from non-unitarity. At the same time, very often in these scenarios, you can actually trade the description of the system between new neutrino interactions and new states. And depending on the exact experimental observables that we're looking for, it might be better to use one or the other description. So very often we can trade between these light new states and neutrino interactions and vice versa in some analysis scenarios. And again, these are all topics that we have to explore in depth to understand what is the right framework to describe a given experimental observable to get the most out of the data. In addition, of course, there could be many other neutrino properties that we can look for and try to understand, which are also connected to some of the others. If you have something like dipole moments for the neutrinos, of course, they are related to the neutrino interactions, and neutrinos might or might not decay, and this might or might not be related directly to a given model for mass generation, let's say, or for flavors. So all of these connections essentially need exploring within each class of model, within each specific model for that matter. And as I already mentioned, here also, every time you discuss new interactions for neutrinos or new states or any other type of properties that you want to understand both experimentally and theoretically, very often within a specific model, all of these will connect back to other types of particle physics, other types of observables like collider physics that, for example, you can use to probe Higgs sectors or maybe some, or lepton number violation, or you can connect to charged lepton flavor, of course, that is in any high energy, any theory that has a scale above electroweak symmetry breaking, obviously the charged lepton flavor will be connected to the neutrinos, but also possibly quark flavors. So this is part of our job in neutrino theory to really explore all the connections between all of these things in enough detail to be able to have actual quantitative predictions that can be tested with the observables. And going the other way around is, given whatever experimental observables we have in different types of physics, not necessarily just neutrino experiments, how can we learn more about all of these properties and their connections? So from here on, I'll focus more on neutrino interactions. And I want to emphasize that actually when I talk about neutrino interactions, we don't necessarily mean new interactions. Even within the standard model, we have neutrino sources in an enormous range of energies. So far, we've detected from MeV to PeV, but we're hoping to get to EV eventually. Even if you stick to PeV, it's a huge range of energies. And we don't understand enough even about these neutrino interactions within the standard model because of this fact that there are many energy ranges, there are many different types of processes, each process is different, and many of them are affected by all sorts of other types of physics, as we'll discuss a little bit later. So even within standard model, we have a lot of work to do to understand, to fully understand neutrino interactions and match them to observations. But even more so, we expect that there are additional neutrino interactions. And again, these happen in many different types of processes, and they might or might not directly quantitative connect to models. In many models, they do. And sometimes we just try to understand them in a more phenomenological kind of way, where we try to experimentally match all possible types of interactions to data and constrain how big this interaction might or might not be. So at this point, before discussing this any further, I want to go back a little bit and remind ourselves what we already know about neutrino oscillations and neutrino interactions. So we have an enormous amount of data from solar, atmospheric, accelerator, reactor experiments, which points us towards a consistent picture of these three flavor neutrino oscillations that we can describe in terms of two delta m squares, three angles, a phase. Some of these we know pretty well, some we don't know so well. So we're still to find what the CP violating phase is. We're still to find what the mass ordering is. And of course, we want better precision on knowing the angles. Just to give you a recent summary of what we already know, as I said, it's the mass ordering that we still only have kind of hints about, and CP violation. Again, we only have some constraints, but not yet full information, as well as how close this mixing really is to maximal. It kind of looks maximal, but we don't know how close to maximal it is. And if it's not maximal, which side of maximal it sits. So these are some of the questions that we ask. So often we talk about the new standard model, which is pretty much just extending the standard model to include just that, to include neutrino mass and mixing that we've observed. But we're still assuming that weak interactions, essentially W and Z exchange, are the only neutrino interactions, and there are no other neutrino states besides the three standard model flavors that we know exist. So in this new standard model, it's very easy to ask these very specific questions of what are those parameters? What are the three mixing angles? What is the CP violating phase? What is mass ordering, and so on. But of course, we have to remember that already assuming that we have mass and mixings cannot be such a trivial extension to the standard model. It is highly non-trivial, just because it's not like the other standard model fermions. We can do the same thing we do there, which is add a right-handed field, just like for everybody else, add a Yukawa, just like for everybody else, while we don't understand why the neutrino mass is so much smaller than all the other masses. Honestly, we don't understand why the electron Yukawa is so much smaller than the top Yukawa already. So maybe that's not such a huge deal. We don't understand why the small mixing angles in the quark sectors are so different from the large mixing angle in the lepton sector. So those are already hints that maybe this is not enough, but that's not what I call non-trivial. The truly non-trivial fact about the neutrinos is that once you've added right-handed fields for the other standard model fermions, there is absolutely nothing else you can do with those right-handed fields. You're not allowed to do anything else besides writing that Yukawa coupling. However, for the neutrinos, you are allowed a Majorana mass term because there is absolutely no symmetry that forbids it, given that neutrinos have no charges, no electric charge, and well, obviously no strong charge. So this is not allowed for any of the other standard model fermions, while for the neutrinos, it is. And as we very well know, if something is not, has no good reason to not be there, if it's allowed by the symmetries, it will typically be generated, it will play a role somewhere or other. So this is what really makes the neutrino mass and mixing non-trivial. And it tells us that either we have to consider the implications of the fact that yes, neutrinos are very different, they're Majorana, which is different from all the other standard model fermions, or we have to understand some new symmetry or some other more fundamental reason why this type of Majorana mass term is not allowed for the neutrinos. So this automatically tells us that there are new interactions and new phenomena. The only thing that we don't know is where exactly these are, what's the right scale to find them. So when we talk about the new standard model, which again still assumes only weak interactions of the neutrinos and only the three standard model flavors, we really think of it as just some kind of effective theory, which is a first step in connecting to the bigger questions of the neutrino mass generation, the nature of the neutrino. And really, we know that those imply that there have to be new interactions and there have to be new particles out there. The only biggest question is, where is that? Again, if it's very high scale, we might not be able to directly measure them. But if they're lower scale, then they could be accessible. So ultimately, really, it's an observational question to tell us what these are. So that's why we need to understand how to actually explore these questions. And I didn't talk about the past experiments. I'm assuming we all know about them. I want to say just a few words about where we're heading in terms of the experimental context, because it's very important. And in the future, there are two major directions that we're really moving into a new era in some sense. One is a very high precision with experiments like DUNE and many others, where we're really trying to essentially move to much, much higher accuracy in measuring just about everything, but also towards very high statistics data in experiments like atmospheric neutrinos in IceCube, deep core, where you have lots and lots of events that you can use to essentially reduce the systematics associated with atmospheric neutrinos and still do a lot of sensitive new physics searches and just standard neutrino property measurements. So we're really approaching a new stage in how we can test both standard neutrino properties as well as new neutrino properties and other types of new physics. But of course, in order to be able to extract the full information from this high precision and high statistics data, we really need to understand theoretically both the neutrino interactions, the analysis framework. So we really need a lot more of this work to make the connection between the quantitative connection between what data tells us and what we can learn about the actual theory side of neutrino properties and new physics properties. So going back to neutrino interactions, which I told you would be the focus of the rest of the talk, I want to emphasize again this statement that I already made, that even within the standard model, there are lots of things that we have to better understand and really work on. And I'm giving here just a few examples. You'll hear more about coherent elastic neutrino scattering in this conference, so I'm not going to talk about that, but it is very relevant to understanding neutrino interactions within and beyond standard model. I'll mention neutrinos double beta decay because that's our best test, experimental test of identifying the nature of the neutrinos, if it's a Majorana or a Dirac.
So Irina, you have about 5 minutes left.
Thank you. And in this type of experiment, Majorana versus Dirac is easy to answer. Once you measure something, you know it's Majorana. But if you want a quantitative connection to actual neutrino parameters, then you need to understand things like nuclear matrix elements, which is much harder. And then as you go to higher energies, you start having all sorts of problems with understanding hadronic physics. And then at very high energies, even just QCD reaches a very new kind of very low X type of parameter space region that we haven't directly probed. So again, these are serious questions that we have to actually spend time on fully understanding. So when we talk about non-standard interactions, we already know about them from the original matter effect paper of Wolfenstein from all the way back in 1978, when he just wrote down a 4 Fermi type of interaction where he parameterized all the possible new interactions of neutrinos with other fermions through these epsilon parameters, which are measured with respect to weak interactions already. And then the question is, well, can you constrain from data how large these interactions can be. And you can think of how these actually connect to theoretical models. And there are many different types of models which can generate such things. Or you can go to data and look at, let's say, matter effects, where these will affect matter effects in neutrino oscillations. And just to give you an idea, the only important point of this table is really to give you an idea that while some of these are of order, constrained to be of order 1, already with current data, some of them are constrained at better than percent level. So we're really probing new scales because we are probing things which are way, way weaker than weak interactions. And of course, in the future, this will get much better. And the other point I wanted to make was that when we talk about non-standard interactions, these vector type interactions that we constrain through matter effect in neutrino oscillation is only just one example, but the idea is a lot more general. We don't know what type of new interactions we might have. It's actually very possible that we can have other types of interactions, scalar, pseudo-scalar, and so on. So we need even further to understand the connections to other types of data, like scattering experiments, which probe different types of non-standard interactions. So overall, we need to really understand all of these connections between actual models and their consequences, or just from data, how well can we constrain the existence of these interactions? And since I'm pretty much out of time, I won't really discuss this example, but what this was really meant to be was just to give you an example of one specific model. So this is just one approach to addressing one of these questions of how do you go from model building to real observations in experiments. And it's just one example of some model which actually asks bigger questions about non-neutrino related issues, like why are there 3 families, and how is mixing generating, and is the 3rd family really special for the quarks? So this was just and also, is low scale physics actually something that could be relevant? Not everything has to be God scale. We don't know. We have to explore physics below the electroid scale as well. So this is just one model of a U1 symmetry that all B minus L, which is nice, anomalies cancel. But because anomalies cancel within each standard model family, we only gauge one generation. So the only point I wanted to make with this model, I don't want to discuss the actual model, but the phenomenology is very rich. And while it generates a new neutrino interaction, this epsilon tau tau here, just because we only gauge the tau sector, you have a new matter effect generated by this new gauge boson, which is now light. But you have a lot of other processes. So once you put them together, if you look at the parameter space, there is some parameter space where actual neutrino oscillations or sometimes neutrino scattering are the most constraining and most likely to be able to probe such models. But then there are 100 other processes. So here it's scattering that shows up. It's not very relevant, but in other parameter space, it might be more relevant. So there are lots and lots of other things. So really, that is what I wanted to emphasize, is that very often when we talk about neutrino theory, it's not a very well-defined question in the first place, what we mean by neutrino theory, because it covers a lot of different aspects and it never lives in a vacuum. You always have to think about neutrino theory in the context of the experimental observables and also in the context of all the other particle physics and astrophysics and cosmologies that we know about. And only when we can understand and actually create a consistent picture of all of these ideas can we truly claim that we know what we're talking about in terms of answering the big questions about both neutrinos and other types of new physics. So I'll stop here. Thank you very much.
Thank you very much, Irina. All right, we have a couple of questions in the chat, so I will go through them in order. So the first one comes from Igor Bernardi, who asks if you could explain a little bit more on neutrino self-interactions in supernova.
Yes, so okay, I can use actually this picture here. It's not the, yeah. So normally when we talk about matter effects, instead of an X here, we have the neutrino interacting through a W with protons, neutrons, electrons, whatever. In a supernova, it would mostly be, well, yeah, so you're looking at a lot of electron scattering in the supernova. And again, just replace this X with W. That's a standard matter potential. What happens in the supernova is that for a little while, even neutrinos with their weak interactions are trapped within the supernova. And there are so many neutrinos in there that in addition, this background, instead of having just electrons, will also, the neutrinos in that background will also be important. So you just have standard weak interactions, W exchange, matter effect, but you will have with neutrinos on both sides. So we're used to the standard matter effect having neutrinos on one side of the W interactions and electrons on the other side of the W interaction. But in the supernova, there are enough neutrinos that actually you can have neutrinos on both sides of the interactions, and the effect is no longer negligible inside the supernova. In regular, in any other environment that we know of, those neutrino-neutrino interactions become irrelevant because you just don't have enough neutrinos and the interaction is too weak. But in the supernova, you have such a high density of neutrinos that the neutrinos become both beam and background. And at that point, you have these nonlinear effects due to this neutrino-neutrino interaction. So it's not new physics, it's very standard physics, but it gets very complex because of the nonlinearity of the process.
Great, thank you. So we'll get to one more before we're out of time. So Sibylla Parveen asks how the fourth flavor of neutrinos affects CP violation of the universe.
Well, so assuming that there is an additional fourth flavor, that would allow for a lot more CP violation. So it's possible to have a lot more phases, which of course we know that one of the conditions for generating, for baryogenesis or baryogenesis through leptogenesis is having enough CP violation. So of course, the more light states you have, the more CP violating phases you have, it is possible to actually generate more CP violation. It's possible to make leptogenesis in principle easier. Of course, having a quantitative prediction is a lot harder and typically very model dependent. So qualitatively, it helps. Quantitatively, it's a detailed model dependent statement.